connecting the host halo and satellite galaxies of the Milky Way.
Hello, everyone. Thank you for having me here, and it's always enjoyable coming back to Santa Cruz and talk to people. And this is my talk. I'm going to present a paper we recently posted on AstroPH and accepted for publication in APJ. The title of the paper is The Connection Between the Host Halo and the Satellite Galaxies of the Milky Way. And this is in collaboration with a group of people. Some of them are here, and some of them are unfortunately not here. When I prepared this talk, I realized actually I can use another title for this talk, the implication of LMC and SMC for the Milky Way. And hopefully I can show why this is a relevant topic for this talk. I will start with some motivations. The Milky Way is our own galaxy. That's why we want to look at the Milky Way not only observationally, but also theoretically. This is our home, and this is probably only galaxy or galaxy system we can observe in a great detail. So if we don't understand other galaxies, we have to understand the Milky Way and the neighbors. And the Milky Way system is also important for understanding the universe. As presented on Monday by Mike, there is a field called near-field cosmology using Milky Way and the local group dwarfs to study cosmology. And also, as many people presented yesterday, dwarf galaxies are probably the best places to understand the galaxy formation physics. And LMC, SMC are significant. This is a two-mass all-sky survey. Other than the Milky Way galaxy itself, the most outstanding systems are LMC and SMC. They are probably landmark of our home. And then it's interesting to understand the implication of existence of LMC, SMC for the formation and the structure of the Milky Way. Add a little bit about methodology. I think the approach is quite straightforward. So we take two suites of n-body simulations of Milky Way-sized halos. One suite is they are all selected within a very narrow final mass range. One is from a cosmological simulation done by Matt Becker. This is a cosmological box with 125 megapascal on site and with decent mass resolution. And from this volume, we select more than 1,300 Milky Way-sized halos. The other suite is done by Mao et al., published in last year, and Yao also presented the work last year here in this workshop. This is a very high mass resolution zoom-in simulation, using this simulation as a parent simulation to select halos. In this suite, we have 46 Milky Way-sized halos. We can do very detailed analysis about the formation history and the structure of the halos, and also subhalos as well. All the subhalos are identified using Rockstar, and the trees are constructed by using consistent tree, all made available by Peter Birozzi here. And I also use a semi-analytical model to make a connection between dark matter structure and the galaxies, which you can observe. And more importantly, in my semi-analytical model, I have a seamless connection between the galaxy formation model and technique to probe parameter space so that we can tightly constrain very uncertain, flexible model to observational data. In this case, Milky Way satellite stellar mass function. So after we make a connection between halos and the galaxies, we can try to gain some insight. So here I'm showing two movies. These are just randomly selected two Milky Way-sized halos from Yao's high-res zoom-in simulations. They are all have very exactly almost identical final virial mass. But if you look at the assembly history, they are very, very different. This one has a lot of large subhalos coming at late time, and this one is established at quite early time. And late time, you only have a lot of small accretion and minor mergers. And if you just look at the main branch and look at the mass accretion history as a function of redshift, all the simulated halos have very different mass accretion history. You have a huge span if you look at early time. And also, this is a concentration history. As the previous talks showed, concentration has this evolution. Early on, halos have fairly low concentration, and with time increases. But the point here is, with very small final halo mass range, you find that the concentration has actually very large spread. Then the question is, which one is the Milky Way? And when we use the Milky Way as a particular case from observation, how we compare observation with model, and which model we should take. And this also large scatter from simulated Milky Way analogs also has a very large scatter in terms of subhalo mass function. Here, what I'm showing is for each Milky Way simulated analog, I can identify all the subhalos and rank order the subhalo by the instantaneous final mass. So this is the first most massive subhalo, second most massive subhalo, and look at the mass distribution of those subhalos. So you see a large spread for every subhalos in the suite of the simulation. And you can make your own model to populate galaxies into those subhalos. And here what I'm showing is the satellite stellar mass function. And the model I use here is my semi-analytical model tuned against redshift 0 field galaxy stellar mass function. And the very same model made Kendall's mock catalog. And what you see here is the prediction is roughly consistent with Milky Way satellite stellar mass function. But the point is there is a very large spread. So the question is then which one is the Milky Way? And the place where we live give us a privilege to observe the system, and how can we use this to constrain galaxy formation models and the cosmology, and the dark matter structure of the Milky Way itself. So first we try to analyze the mass accretion history of those halos, and this is a one random case selected from the suite of the simulation. And the solid lines are simulated mass accretion history of the Milky Way host. Different colors are different resolution. They agree very well. And you can use this mass accretion history fitting formula to describe this mass accretion history. And actually, this one was used by this author a few years ago to fit millennium simulated halos over very large range, but we use this only to study the Milky Way. And this actually is a combination of pretty proposed fitting formula by Weschler et al. And Vandenbosch et al., just different parts, exponential or power law. The merit of this fitting formula is, actually, if you look at this formula more carefully, they have a very useful asymptotic behavior. Approaching redshift 0, this parameter combination, beta plus gamma, tells you the accretion history at redshift 0. So by looking at this fitting parameter, you know how fast the halo is accreting material at redshift 0. Here I'm showing the distribution. This is all the Milky Way analog simulated halos, and you find they are populating a particular region in this parameter space. And the one beta plus gamma is higher, that means this halo is accreting faster at the present day. And if you go that way, that means the halo is accreting faster at early time. So halos don't randomly distributed in this diagram, but they occupy a particular region. And more interestingly, if you look at the circles have sizes, and the size really mean RS. To help you understand this diagram better, I show concentration and this recent accretion rate. So these halos are lower concentration and faster accreting, and these halos have a higher concentration but slowly accreting at the recent time. And more interestingly, and you can see colors. And the color means the mass of the most massive subhalo hosted by those halos. And what you see is actually faster accreting, low concentration halos tend to host high mass subhalos. So all these things are correlated, as demonstrated by this diagram. Whether the halo is rapidly accreting at daytime and the concentration, and also the high mass subhalos. So then we can, basically we have prior knowledge about the halo, but we don't understand which one is the Milky Way. So then what we do here is we split the sample into two parts, low concentration, high accreting halos, and slow accreting, high concentration halos. So when you split the sample, you'll see two different groups. The blue group and the red group. They have different characteristic mass accretion histories and also the way they increase their concentration. And when you do that, you also find that their subhalo mass functions are systematically different. And the halos have rapid accretion history, lower concentration, tend to host the more high mass subhalos. And that will have implication about the galaxy formation. Here, I use the MCMC to probe the parameter space of the galaxy formation model, but constrain that model to observe the stellar mass function. And you find that the model is accurately constrained. The model can reproduce the mass function very well. However, because this is a particular mass range, you don't necessarily get very strong constraint on many parameters. For example, star formation efficiency and how outflow is doing in terms of reaccretion, so on and so forth. However, there is a very strong constraint on the mass loading factors. Later, I will come back to this. But the point here is if you use another group of halos with higher concentration, slower accretion rate, you can also get a quite decent constraint. You can also reproduce the mass function to a very large extent. And the behavior of this group is also similar, but have some differences. As I show here, the strong differences are in this mass loading factor. Later, we will come back to this point quickly. And the point here I want to emphasize is you have to understand your halo prior very accurately. Although you have a very accurately constrained model, but you miss out the underlying merger tree, you make a very wrong prediction. So although the blue and the red models are well calibrated, but you use the wrong tree, then you find that none of the model can reproduce the mass function anymore. So then it's very dangerous to judge a model if you are using a wrong tree. Coming back to here, you find a very strong constraint on mass loading factor. What that means is actually it tells you a very peculiar mass scale or velocity scale, 32 kilometers per second. The implication is the mass loading factor for this particular velocity scale has to be 300. Why is that? So it seems this simulation suggests this velocity scale is very, very interesting. Something must be going on. And it's very also interesting to look at because the models are constrained to have a very different feedback prescription. They also predict a very different metallicity stellar mass relation. For the red model, because we do need very strong feedback to suppress the star formation in very massive subhalos, the metallicity is relatively lower. So what that means is if you understand the physics of feedback, you can use metallicity relation to understand the subhalos. And also we make a prediction about small subhalos brought by LMC and SMC. Those different halo priors give you very different prediction. What that means is if you look at small satellites nearby LMC, and if they are physically associated, you can tell the mass of the LMC and SMC systems, and also statistically constrain the host halo of the Milky Way. Same thing we also find for the central galaxies. Not only the halo prior influences the subhalo population and satellites, but also central galaxies. High concentration halos tend to host a high mass central galaxy for given halo mass. So this is probably the halo assembly bias effect found in many abundance matching and halo occupation models. So these are pretty much what I want to present, and I leave my summary slide here, and I would like to take questions.
Thank you. We have a couple minutes for questions.
Is there any difference in the mass of the largest subhalo ever accreted at infall time?
Life of the subhalo. What do you mean?
The largest subhalo ever. So if I understand correctly, you're showing that things that build recently have large subhalos today, right? Which makes sense because they haven't been destroyed or stripped yet. But if you look at the largest subhalo, basically the merger statistics.
So this is a very good point. Although we didn't include that part of the analysis in the paper, but we do see trends. More massive existing subhalos tend to be accreted fairly late.
Yeah, I was wondering if there are other observations that could tell us what kind of halo the Milky Way lives in, except for the satellite population, whether it's a slower accretor or a fast accretor, some other independent observation.
As we show here, not only accretion history, but also concentration. So concentration is a pretty good indicator about the accretion history. But the problem is in observation is quite, I don't mean to show here. So you can, you have some kinematic constraint about the Milky Way. So you can have some understanding about the structure of the Milky Way halo, observationally, those points. But the point is, we are analyzing n-body simulations, and when you want to compare the predicted kinematics of the Milky Way, you have to consider baryon. So when you consider baryon, not only you are adding baryon component from the dotted line to dashed line, but also contraction effects from the dashed line to the solid line. So when you consider all this, the concentration, apparently, the concentration is boosted significantly. So that's why using observation, you see the Milky Way has very high concentration, but in simulation, you rarely see those for Milky Way mass. What?
Concentration of dark matter concentration of the Milky Way is somewhat
from simulation, exactly.
No.
That's
Mass modeling of a Milky Way galaxy.
Yeah. So here,
okay.
this is.
Well, this is
exactly. This is through doing mass modeling. So you have n-bodies predicted structure of the dark matter, and then you assume galaxy formation in the middle. Then you can model the mass distribution. Then you get this color bands.
But
so the point I want to make is that they are all consistent with observation.
This sounds like a lovely coffee discussion topic. So let's thank you, Lou, and this morning's speakers.